Hello, my name is Gerardo Roda Vique, and I'm a PhD student at the University of Sheffield. Today, I will be presenting our paper with John Barker titled The Use of Voice Source Features for Sung Speech Recognition. In this paper, we ask whether voice source features such as the pitch, degree of voicing, and voice quality features can help improve automatic Sung speech recognition performances. We argue that conclusions drawn from studies on spoken speech may not be valid on the Sung speech domain. Why are we working on Sung speech? Well, there are several applications for music information retrieval. Just a few examples: retrieve the song's lyrics by recognizing a segment of a song, or retrieve some information like the author, the title, and the album just by singing a small part of the song, or indexing a music collection using lyrics keywords. Beside the music information retrieval applications, Sung speech is inherently less intelligible than spoken speech, and misheard lyrics are very common. So, learn how to adapt speech technologies to Sung speech may provide us with some insight into how to adjust to other types of less intelligible speech signals, like didactic speech or perhaps even casual speech. The rest of the presentation is structured as follows. First, I will presenting the motivation of our paper. Then, I will presenting an analysis of the challenges of Sung speech recognition and how the vocal source features may be useful to alleviate those challenges. Last, I will be presenting recognition experiments comparing the performance of a baseline system using traditional ASR features with systems using augmented feature vectors with voice source-based features. Our motivation. Successful ASR systems for spoken speech are traditionally trained using captual features like MFCCs to capture the characteristic of the vocal filter. In addition, these systems use some sort of speaker representations like I-vectors that help the ASR's performances by conditioning the models. However, since Sung speech is less intelligible than spoken speech, much poorer performances are obtained when we use just these representations for Sung speech recognition. In spoken speech scenarios, both source features like pitch and degree of voicing help to improve the discrimination between voice and unvoiced sounds, or by exploiting the relationship between the pitch and the vocal tract for vocal tract normalizations. Now, I will presenting some of the challenges we face when dealing with Sung speech and how the vocal source features may be useful for Sung speech ASR systems. For this analysis, we utilize the NUS 48E Sung and Spoken Lyrics Corpus. The corpus is composed of Sung and spoken lyrics of 48 songs from 12 speakers. The dataset possesses speakers from American and Singaporean accents. The difference in accents may result in a larger variability on the spoken speech production than on the Sung speech. This because when singing, the native English speaker accent tends to neutralize, and there is a tendency to move toward American pronunciation. So first, using the NUS 48E corpus, we compare the vowel duration between Sung and spoken speech. In spoken ASR, the duration of a vowel can aid to discriminate between short and long vowels, like in beat and beat. In this plot, we can see that the duration of the spoken short E is concentrated in about 100 milliseconds, but the long E is more spread, reaching values as long as 500 milliseconds. However, in singing, as we can see in the figure on the right-hand side, a vowel can be extended much longer than with speaking. This to achieve the rhythm dictated by the song. The differences in the vowel duration invalidate the duration as a discriminator between short and long vowels. It's been shown that extended Sung speech vowel durations can lead to insertion and substitution recognition errors, especially if pitch varies during the vowel. As I mentioned before, the voicing degree can help discriminate between voiced and unvoiced sounds, like in price and price. In this figure, we can see the probability of voicing from the spoken voiced and unvoiced fricative pair measured using the CALDI toolkit. Here, smaller values mean more strongly voiced. We can see that there's a significant overlap between degree of voicing of both phonemes, with several voiced sounds pronounced more voiceless. We hypothesize that in singing, the speech might be more heavily voiced in order to carry the melody, which may difficulties the voice and voice discrimination. However, for Sung speech, voice sounds show a greater voicing degree, which let a higher batch area distance in comparison with the distance of the spoken sound. This may suggest that the degree of voicing can, in fact, be more helpful for swing speech than for spoken speech. However, for the case of plosive sounds like P and B in pig and big, we found that when singing, the P's are pronounced slightly more voiced than in spoken speech, and the B's are pronounced with a more consistent voicing degree, making both sounds less distinguishable in swing speech. This may limit the use of voicing degree as a discriminator to certain groups of phonemes, like fricative sounds, and not be as helpful for plosive sounds. Then we evaluate the differences in the pitch ranges. This plot shows the pitch ranges between genders and the two types of speech styles. From this plot, we can see that there's a clear distinction in the spoken pitch range per gender, with a small overlap. However, these ranges are much larger when singing, existing a large overlap between gender. This large range implies that virtually a singer can have different voices when singing at different frequencies in their vocal range. This can affect the role of the I vectors as a speaker normalization in ASR systems. Therefore, inform the models with the pitch can help to conditioning the models to speaker at different pitches. For the voice quality parameters, we analyze the jitter, shimmer, and harmonic to noise ratio. These are common parameters for voice pathology detections. Jitter measures the frequency variation between cycle to cycle. Shimmer measures the amplitude variation of the sound wave, and the harmonic to noise ratio measures the ratio between the harmonics and the glottal noise. These plots show the parameters central tendency and error bars per gender and how they vary by speech style. These parameters show some gender and speaker correlation in the spoken speech, being the jitter and shimmer ranges higher and H&R range lower than in swing speech. These parameters lost most of their gender differentiation in swing speech, possibly weakening their value for speaker normalization. These variations between speech styles can be explained by, first, after the vocal tract muscles warm up, the jitter and shimmer reduce their values and H&R increases. Second, jitter and shimmer have different level interaction with different types of frequency oscillations like vibrato and trilo, depending on how trained is the singer. Last, these parameters are correlated with the fundamental frequency. Jitter reduces its value as higher frequencies. Therefore, these parameters can help to conditionate the models to singing conditions. Now, I will present experiments and results on using the vocal sort features for ASR systems. For the ASR experiments, we use the DSync dataset and accompanied swing speech dataset for ASR based on the SMUL corpus we presented in previous work. DSync provides three increasingly larger training sets, DSync 1, DSync 3, and DSync 30. The smallest DSync 1 possesses 15 hours of speech of singers from Great Britain. The second set, DSync 3, expands DSync 1 by including singers from America and Australia, increasing the data to 44 hours. The largest, DSync 30, includes all English spoken songs from the 30 countries containing the SMUL datasets, totaling 150 hours of sung speech. DSync also offers two testing sets of roughly 45 minutes each, one for development and one for evaluation. All singers in both test sets are from Great Britain, and the singer and songs arrangements are not included in the training sets. Our baseline was constructed by using the CALDI toolkit. To construct an in-domain language model, we collect 44,000 lyrics from unseen songs from all artists in DSync 3, plus artists in the Billboard, the Hot 100s. Using a vocabulary of 28K most common words, we train a 3-gram and 4-gram maximum entropy language model. For the acoustic model, we train a factorized TDNN with lattice-free MMM objective function using 40 MFCC plus deltas and 100 I vectors with 3 frames of context. Experiments for the baseline were trained 11 times to obtain a 95 confidence interval and were evaluated in terms of the word error rate. Here we can see that 4-gram models perform better in all scenarios. Also, we can see that there's a clear benefit of training the model using the largest Desync 30, reducing the error from 38 in Desync 1 to 19 in Desync 30. Note that this improvement was obtained despite that this Desync 30 contains a large variety of accents from native and non-native speakers from 30 countries. The vocal sort features were evaluated by retraining the acoustic model from the baseline by increasing the MFCC feature vectors using the pitch and degree of voicing in the first experiment. The second experiment increases the feature vector further by including the 3 voice quality features. These experiments were also run 11 times to obtain a confidence interval. This table shows the ASR results from the baseline and the 2 experiments described before. First, for the Desync 1 dataset, using the pitch and degree of voicing reduces the error in 1.5% when using the 4-gram language model. Similar performances was obtained when expanding the vector further using the voice quality features. For the Desync 3 case, we observe a reduction of 0.7% when using the pitch and voice quality features. And for the Desync 30, no voice source features, resulting in statistical significant reduction of the error. One possible reason for this is that the model may be able to learn phonetic cues being carried by the vocal source in an indirect manner, for example, via the temporal dynamics of the MFCCs. Conclusions. Sung speech is a less intelligible kind of speech that differs from spoken speech in vowels direction, level of voicing, in voice and unvoiced pairs of consonants, and possesses a large pitch range. When evaluating voice source features, we found that the use of pitch information and the degree of voicing helps to reduce the error when using small size resources like Desync 1. However, we don't observe this benefit when using largest datasets. We hypothesize that given enough data, the cues being provided by the vocal source features can be learned indirectly from the conventional MFCC parameters. Thank you so much for watching. I hope you found this work as interesting as we do.